Thank you very much, Bea, and thank you for the presentation, and thank you everyone in the room for being there and paying attention to this little short presentation about this work that I did during my PhD. And the summary of this work is to talk about a specific embedded boundary method for simulating fluid and structure. This, in particular, is done for simulating rigid hard valves. So I hope you enjoyed the presentation. For that, let me start with the general problem. So we have a solid, we have a fluid domain, but one of the key of this kind of method is that the discretization of the fluid doesn't take into account the solid, okay? This is one of the main keys of this method. Then for one side, we have, of course, the fluid that we have to model. In this case, we use the incompressible Navier-Stokes equation that you seen in the screen when U is as you know, the velocity, P is the pressure. And also we have, of course, the strain, the epsilon that is the strain, and the omega that is the stress tensors. So normally in a fluid problem, we have two kinds of boundary conditions. Dirichlet and Neumann, okay? So, but in our case, in this special problem, we have a new boundary Dirichlet condition. This new Dirichlet condition that you can see here is impose the velocity of the fluid on impose the velocity of the solid on the fluid, okay? This is for the fluid. On the other side, we have the solid physics that we have to solve. And as you already know, this is a rigid solid. So we only need to solve the Newton-Euler equation that is showing the screen, where the force and torque that are in red here in the screen come from the fluid. So for doing to summarize this question, so the fluid needs the velocity that comes from the solid, and the fluid gives the force to the solid. Okay, so as I already said, one of the key of this embedded boundary mesh method is that the discretization of the fluid doesn't take into account the discretization of the solid, as you can see in this square here, okay? So at the end, what we have to do is to remove, as you can see here, the elements that we will consider, the elements of the fluid, that we will consider as part of the solid. So now, in this red line that I'm pointing you, we have to impose the velocity of the solid. So let me show you all the process. So we have a solid, we have a discretization of the fluid. The discretization of the fluid does not take into account the solid domain. Then at some point, at some time step, so the solid moves because, of course, for the force and torque that comes from the fluid. And at one time step, we have to find the elements of the discretization of the fluid that we will consider part of the solid. In this case, these gray elements that you are seeing in the screen. And as I already said, we have this black line that indicates the new internal boundary that is created inside the fluid that we have to put the solid velocity. This is for the elements, of course, but also for the nodes, we have to create like different fluid nodes. So we will have these red nodes that are very important because they are part of this new boundary that is created that will indicate to the fluid that this is the division between the solid and the fluid. We have these black nodes here that indicate the fluid nodes, and these white nodes inside the circle that are the solid nodes. Okay, so at the end we will have that. What is that? So we have to remove the elements part of the solid that we will not take into account on the assembly process. Also, we don't take into account the nodes that are inside the fluid. Okay, this is for a one-time step, and we have to think that at each time step, this configuration will change. Okay, so now how we impose the solid velocity to the fluid. So for that, we will consider this node here that I'm showing you to indicate the process. So the first step that we have to do is for this node, so we have to repeat this process for all the nodes that are part of this interface. For this node, we have to find the projection point. The projection point of this node on the surface body, as is indicated in this figure. Then we have to select an element. This element that is here, of course, this is an element that is part of the fluid. This element has to have some conditions to be selected, as we have to find an element that we will maximize the number of nodes that we will select for the interpolation. I will explain that later. And also we have to take into account that this element, we will have some properties that I will explain later, okay? But for the moment, we have to think that we have to select a convenient element. Then with this element, once we select this element, we can select the nodes, okay? So which node we will choose? The element that we will choose is the node, sorry, that is, as you can see here, we have the elements. So we choose the nodes that are part of the element, but also the nodes that are connected to each one of the nodes of the element, all these black nodes. So now I can explain a little bit how we have to choose this element. This element is chosen in a way that we have to maximize the number of nodes, these black nodes, okay? And also we have to minimize the distance of these black nodes to the node that are selected, that we are working in this moment, okay? But why we have to do all this selection of these nodes? Because at the end, what we want to do is to approximate the velocity at this node using what? Using all the selected nodes, all the velocities on the selected nodes and the velocity on the projection node, okay? So for that reason, we have these coefficients, these n coefficients that we have, of course, to calculate. For that, for calculate these coefficients, we will use a method that is calling Kriging interpolation. And more or less, I don't want to enter in details about this interpolation, but only some global concept is the idea of this method is to minimize the error of the approximation. This is the error of approximation because this is the actual value of the velocity, and this is the approximation, okay? So we have to minimize the variance of this error subject to this condition. What is that condition here? This condition means that the mean of the error has to be 0. What's that? This is an ambiguous condition. So this is very important to complete. So this is a problem of minimization, this variance of the error of the approximation subject to this condition, okay? Okay, this method can work, but we have to think about the parallel implementation of this. For that, let me show you some illustrations. This selection has a problem in parallel. And I will show you that doing this illustration. So imagine that we are working with this node N, and we have this node connect to this node N, these black nodes here, and we have the elements connected to this node, that gray one. So in parallel, in our implementation, what we done is to do a partition of the mesh in such a way that each element of the subdomain belongs to only one subdomain, okay? This is our partition. But what is the problem of this kind of partition is that if, for example, the node that we are considering here, this N node, what is the problem? That right now, the elements connected to these nodes are defined in different subdomains, and also the nodes connected to these nodes are defined in different nodes. So if you remember our selection algorithm, we need all the nodes that are connected to each node of the selected element. So in this case, we have a problem because we don't have this data. Of course, a lot of different solutions can implement it. But in our case, our solution was to add data from other subdomain such that for each node in a subdomain, all the data of the connectivity, node connectivity, and element connectivity is available, okay? We opt for this option because in this way we can reduce the number of communications. So as you can see now, with this kind of parallelization, doesn't matter which element we selected, we will have all these nodes, all these black nodes, all this data we will have available in any subdomain. With respect to the body data, because we are in parallel, okay? So our solution was to do all that. What we're trying to do is to have all the data of the bodies in all the subdomains. Okay, of course, this kind of solution is not so parallel because we have the same information for each subdomain. So you can imagine that if we have 2 or 3 rigid solids, each data of this rigid solid will be shared for all the subdomains. So of course, redundant work will be performed, redundant work we will done, but in this case it's okay. And why is it okay? Because if we take into account that solving a fluid is much more complex than solving, of course, a rigid body equation, and also we will have to take into account that the mesh of the solids are in general is very, very, very small in comparison with the meshes that we will have on the fluid. So this redundant work is okay. We will not affect, or we will affect so little to the general performance of the time of calculation of the simulation. Okay, now the question is how we impose the force that comes from the fluid to the solid. Remember that the fluid is described by the Newton-Euler equations. At the end, after a discretization in time and in space, we will have this linear system of equation. This linear system equation is very easy to understand. The only particular thing about this discretization is that we separate the velocity and the pressure variables, okay? So this is the reason why we have this matrix A 4 times, and this is the reason why we have 2 right-hand side vectors, okay? But it's like any other discretization. So we only separate the velocity from the pressure. At the end, the idea is to use the residual of the velocity. This is why we are using only the first row. We are trying to use this for calculate the residual that will give us the force and then the torque of the solid. But this is very, very important to say that, of course, we have to calculate this residual only for the nodes that are part of the interface in this in the fluid discretization. Okay. The reason that to use this kind of residual instead of, for example, integrating, that is a more directed solution, is that as we can see in this very simple example, the green line that represents this way of calculate the force that will be imposed on the solid reach much faster the real force than, for example, integrating, that is representing this red line. Here you can see how the mesh is refined, and we can approximate faster from the residual way to calculate the force. Okay, so now let me talk about the result that I want to show you, the most important thing in the presentation. So what we want to simulate is this artificial aura. We have here 4 sections, okay? In the first section, in this A section, is the input of the fluid force. As you can see, this is an impulse that represents more or less a heart impulse. Here there is located the rigid valves. As you can see here the valves are located in the middle of this section B, and there here you can see a zoom how the valves open and close. Okay. And then you can see the velocity and vorticity. One very special thing about this simulation is that the velocity allows us to open the valves. But as you can see here in the vorticity, it's thanks to the vorticity that the valves can close. Because even if we have a reverse inflow at the end of the pulse for a heart, this reverse impulse is not so strong to close the valves, okay? Here you can see how these vortices can grow near to the sinus of this artificial aura that make this turbulence grows and close the valves for different positions of the impulse. And this last slide shows us maybe this is the most important slide of the presentation, because here we can compare the real experimental data with our simulations. As you can see, this is the angle of closure of the valves. You can see that the blue dots indicates the experimental data, and the red and green lines indicates the simulations. As you can see, the simulations are good enough. But this fine mesh that is 12 million elements is closer to the experimental data than the coarse mesh that is the red line. Of course, both are okay. So thank you very much for your attention. And if you have any question, I will be glad to answer you.